Hello friends, welcome to my channel. In this video, I will cover GATE previous year papers, Strength of Material, Design of Machine Elements and Engineering Mechanics 2016 Set 2. Question number 33, 34, 35 and 38 all are 2 marks question. I will solve. Question is a simply supported beam of length 12 is subjected to a moment of m at the midpoint x equal to 0 as shown in the figure. The deflection in the domain x is less than equal to x is less than equal to L is given by, so Wx given, where E is the Young's modulus, I is the area moment of inertia and C is a constant to be determined. The slope at the center x equal to 0. Slope at center we have to calculate. Here we will use moment area method. So first reaction we will calculate. For reaction, horizontal reaction, summation of all horizontal forces, it should be 0. Here no horizontal forces. So then for vertical forces, mark the points A and B, then center C. You will get two reactions here, RA, here RB. So it's equal to 0. RA plus RB, it's equal to 0. Both are unknown. RA, it's equal to minus RB. Then take moment along A point we will take. Moment along A point, MA, it should 0. Clockwise moment we will take negative, means like this we will take negative, like this it's positive. This distance is LL, summation of all forces, or moment along A it's 0, RB into 2L plus moment also anti-clockwise, both are positive, it's equal to 0. RB equal to minus m by 2L, and we know it should RB equal to minus RA, so RA equal to m by 2L. Then from B to C we will calculate XX. At XX, let this distance is x. Mx moment at XX, it's equal to, it's positive RB into x is the distance. So at B point x equal to 0, MB at B point moment is 0. RB into x is 0, so MB equal to 0 at B point. Then if you check at C point, when x equal to L, at C point it's RB into L. RB into L, and we know RB we already got, it's minus m by 2L into L. L we can cancel, it's minus m by 2. At C point it's minus m by 2. And if you start from left side along AC, at x distance, XX section, you will get mx equal to, it's also positive, RA into x. At A point, moment at A point, it's x is 0, so RA into 0, it's 0. At C point, x equal to L, it's RA into L. RA into L, RA is m by 2L into L, you will get m by 2. Once you are getting minus m by 2, and second time you will get plus m by 2. So if you do your diagram, it starts from 0, moment diagram, bending moment diagram, you will get like this. Two similar triangles. Here m by 2, 0. This side also m by 2. We got our bending moment diagram, and moment area method we will apply here. We know deflection is A into x bar divided by EI. A is bending moment diagram and x bar is distance of CG. So here in this diagram, CG will come here at this point G, and its distance is 2L by 3, because this distance, it's L distance. B to C, it's L, so it's 2L by 3. X bar is 2L by 3. So we will calculate delta C. Deflection at C point, it's 1 by EI into your bending moment area, half base into height, minus half into base is L, then height is m by 2 into your center of gravity distance, CG distance, 2L by 3. Then it's 2 cancel, then minus into minus, it will become positive, ml square by 6 EI. This is delta value, delta at centers, deflection at centers. Then for slope at C point, it's equal to delta C divided by length, ml square by 6 EI to 1 by L. You will get ml by 6 EI. So from option we will check. At C point we have to calculate. At C point, slope at ml by 6 EI. Question is, in the figure the load P equal to 1 Newton, length L equal to 1 meter, Young's modulus E equal to 70 gigapascal, and the cross section of the link is equal to square with dimension 10 into 10 mm square. All joints are pin joints. The stress in Pascal in the link AB we have to calculate. Stress sigma AB we have to calculate. So P is like this, means FBC you will get here, and FAB, this is FAB. Or free body diagram you can write like this. P is in this direction FAB, this direction FBC. Angle also given 45 degree, this angle also 45 degree. Both are collinear, so P equal to FBC. And if you remember truss formulas or truss examples, if two forces are like this, they are collinear, other force is acting like this, the other force, first force, second force, if they are collinear, and third force, it's acting like this, so third force will become 0. So F3, F1 and F2 both are same, they are collinear, and F3 it will become 0. So if you apply Lami's theorem also you can solve, same answer you will get. FAB equal to 0. We have to calculate sigma AB. Sigma AB is FAB divided by force by area of AB. Already force AB it's equal to 0, so sigma AB it's equal to 0. Directly also without calculation you can solve this question. It's 0. A circular metallic rod of length 250 mm is placed between two rigid immovable walls as shown in the figure. The rod is in perfect contact with the wall in the left side and there is a gap of 0.2 mm between the rod and the wall on the right side. If the temperature of the rod is increased by 200 degrees Celsius, the axial stress developed in the rod is, in MPa you have to calculate. Young's modulus of the material is 200 gigapascal and the coefficient of thermal expansion alpha is 10 to the power minus 5 per degree centigrade. So, if there is no barrier, let the points will A, here B point, then C point. Let the rod without any barrier at C point. If there is no barrier, if you hit it, then it will expand like this. If there is barrier, if you put barrier, it will expand up to C point. C point initially, at B point it will expand up to C. So this much length it's contracting or compressing. Let this is D point, CD you are losing. This is B, then here C, this is D. Up to D point, if there is no barrier, up to D point it will expand. If there is barrier, you will lose CD. Up to BC, it will expand. So first, without barrier we will calculate. We know thermal strain, it's alpha into delta T. Alpha is coefficient of thermal expansion and delta T is your increase in temperature. So here we will get del L. This is B to D. B to D it's alpha delta T into total length. Total length is A to D. A to B, initial length we have to calculate. We have to consider initial length. L is 250 mm. So, then with barrier we will calculate. We know with barrier del L is PL by AE or its stress into L by AE, sigma into L by E. This is the restriction CD with barrier. This is compressive stress sigma. Due to compressive stress sigma, we are losing the expansion up to D. So CD expansion we are losing. So delta L CD equal to PL by AE. It's equal to sigma L by E. Sigma is our normal stress. So our gap is B to C. B to C is BD minus CD or del L BD minus del L CD. Or we can write, already we got, it's alpha change in temperature into length minus it's del LCD due to axial stress or compressive stress you can write it axial stress by E into L. Then gap already given, it's 0.2. In meter we will calculate. Alpha is 1 by 10 to the power 5 to delta T is temperature, change in temperature is 200 degrees Celsius. L is 250 minus sigma A divided by E is 200 into, it's in gigapascal, so 200 into 10 to the power 3 into 250. So then 0, 0, 100, 250,000, it's 4. So if you solve this one, you will get 0.2 equal to 0.5 minus sigma A divided by 800. Again, sigma A equal to 0.3 into 800, you will get 240 megapascal. This is your answer. So fill in the blanks type question. 250 megapascal. First you have to consider, without this barrier it will expand up to D point, and because of axial stress this expansion is restricted up to B to C only expansion, and CD, this expansion you will lose due to this barrier. So one axial stress is there which is restricting this expansion up to D point. So you have to consider this one, gap equal to del LBD minus del LCD. Question is, in a structural member under fatigue loading, the minimum and maximum stresses developed at the critical point are 50 megapascal and 150 megapascal respectively. The endurance, yield and the ultimate strength of the material are 200 megapascal, 300 megapascal and 400 megapascal respectively. The factor of safety using modified Goodman criterion is how much? So modified Goodman we have to calculate. So your data given are maximum and minimum stress. Sigma minimum, it's 50 megapascal. Sigma maximum, it's 150 megapascal. Then sigma E, its endurance strength 200 megapascal. Then yield stress sigma Y, it's 300 megapascal. Then ultimate strength, it's 400 megapascal. We have to use modified Goodman criterion. So sigma B versus sigma mean. Modified Goodman, first here modified Goodman means here it's sigma E, this side sigma U. Modified Goodman, you have to divide factor of safety. For modified Goodman, our formula is sigma mean by sigma ultimate plus sigma variable divided by endurance limit stress, this equal to 1 by factor of safety. We have to calculate factor of safety. First sigma mean we will calculate, its maximum stress plus minimum stress divided by 2. Maximum stress given, it's 150 plus minimum is 50 divided by 2, it's 100 megapascal. Then sigma variable V is maximum stress minus minimum stress divided by 2. 150 minus 50 divided by 2, 100 by 2, it's 50 megapascal. Then here we will put the value sigma M 100 divided by ultimate stress is 400 plus variable is 50 divided by endurance limit already given in this question, is 200, it's equal to 1 by factor of safety. So 1 by 4 plus 50, 1 by 4, 1 by factor of safety. If you solve this one, you will get factor of safety, it's equal to 2. This is your answer. So from option D is your answer. This is the end of paper 2, strength of material, design of machine elements and engineering mechanics. Thank you friends. Thank you for watching my video. Thank you.